Our lesson for today, oops, sorry, here we go. Our lesson for today is applications of electromagnetism. Um, if we could do this live in person, I'd literally get things out so you could see them. So for this video, I'll talk you through it as best I can virtually. I've given links so you can see other resources, but really, especially these first three, it's just to give you an idea of how electromagnetism would work in the real world. I'll do my best to talk you through it, but as long as you have a general understanding, it's not, I'm never going to ask you to like draw a doorbell, but maybe in the real world, if you had to take apart your doorbell and you saw all this stuff, you'd have an idea of what was going on. With that, I'm going to start with the doorbell. This little emblem up here by letter K is the button, the symbol for a button. So when you push the button to turn on the doorknob, we've got a battery in it. So what happens is when you push the button, current flows through those red wires and into the kind of important thing in this diagram is E. So this sort of upside down U-shaped thing at E, when a current flows through those red wires, these red wires here, basically they're coils with a metal core. So E becomes an electromagnet when the button is pushed. When E becomes an electromagnet, it attracts this chunk of metal over here to get closer to it. So this chunk of metal gets pulled upward, just a magnet attracts another magnet. When that happens, this whole long arm moves, and this little hammer at the end moves up and hits the bell, makes a little ding sound. However, what was really clever about it is when that arm labeled A, when it moves upward, sorry, I gotta draw some more, down here by T, when it moves upward, it physically breaks contact. So the circuit, so that little wire above this little nail looking thing, they're touching, but when A moves upward, they stop touching. So since they stop touching, that breaks the circuit, and E is no longer a magnet. Since E isn't a magnet, then that arm A falls down and away from the bell. When it falls down and away from the bell, it remakes contact down at T again. When it remakes contact, that makes E a magnet again. That lifts the hammer up and it hits the bell again. So depending on the nature of your doorbell, sometimes they're different with how they work with a button. But basically, it's got this electromagnet that pulls the hammer up, hitting the bell, and then the act of pulling it up also disconnects the circuit. And this one is labeled as T. And in disconnecting the circuit, that turns it off so it falls back away from the bell. And the act of falling away turns itself back on, so that pulls it back up. So we get this binging up and down against the hammer hitting the bell over and over again to make the doorbell go. Check the link out, but that's kind of in a nutshell how a doorbell works. Speakers have come a long way, but a very rudimentary speaker has a permanent magnet back here. So this thing back here is a permanent magnet, including this part kind of in the middle that runs in between this coil. So this thing in here, I'm shading black, that's a permanent magnet. It's got a north pole, maybe here's a north, and maybe over here's a south. Sorry, a little messy. So that's the permanent magnet. I gotta get rid of that. In these blue wires, these wires, it's not showing the connection, but these wires would somehow go out of here and connect to whatever you're listening to. Your phone, an amplifier, your TV. So these would connect to whatever the source of the sound is. So like they would have a headphone jack at the end, let's say, old school, or somehow a Bluetooth communication would tell the source what to send, what electricity to send down these wires. So in these bluish purpley wires, it's going to send electricity back and forth in a sort of a complicated Morse code. As the electricity woggles back and forth, that turns this coil into an electromagnet. Maybe for a split second there's a north pole here and a south pole here. Then maybe a split second later it switches so that there's a south pole, so that there's a south pole here and a north pole here. So as that current switches back and forth, the electromagneticness of the coil switches back and forth. What that does is, in one particular direction of current, that pushes this cone outward, and then a split second later, when it switches magnetism, that pulls the cone inward. So the source sending this sort of complicated Morse code electric signal, the end result is that this cone part wobbles back and forth. And as it wobbles back and forth, sorry, I'm going to mess up my own diagram, that creates, last unit, these high pressures and low pressures that we know as sound waves. So it's this squishing back and forth, the moving back and forth of the cone. The springy supports are just there to keep the cone kind of centered in its sort of resting position. And as the cone wobbles back and forth, based on the electricity running through the coil, being close to a permanent magnet, that forces that cone to move back and forth. That's what creates those pressure waves that we call sound. The last one, realistically, this is probably the most important one. This is how we can start our gas-powered cars. This is how elevators, electric toothbrushes, hard drives, pretty much any motor that spins is based off of this idea. Really what we've got, so as you've seen in all our applications, we've got a permanent magnet. So the way this one's drawn, we've got a north pole over here and a south pole over here. And then we've got electricity run into a coil. In our electric motor, the coil exists kind of in between. So here's my coil. The coil exists in between the north and south pole. And this one, it looks like there's two wrappings on the coil, but there could be a whole bunch of loops of wire in between the north and south. The other thing that happens is we somehow need to send electricity into the coil to turn it into an electromagnet. There's other things going on. This one's labeled with a split ring commutator and brushes. Those are just clever ways so that when the coil spins, it doesn't tangle the wires. So those are just a clever solution so that wires don't get tangled. There's a couple ways to think about the direction that an electric motor will spin. I'm going to do this one with sort of the left-hand, right-hand rule for a coil. So let's just focus on the coil, and I'm going to do right-hand rule. Positives go from here into this brush thing, and then from the brush thing they go into this thing that's labeled a split ring commutator, and then they go this way. So positives are going that way, then they're going that way. When they're at the back, they're kind of going to the right, don't really care about that. When they're by the south pole, they're coming kind of towards you, and then they loop around, commutator, brush, kind of complete the circuit. If we just focus on that coil, if we did right-hand rule, so positive flow, right hand, when your fingers are far away from you, so this part of the wire, they need to be moving to the left, or sorry, to the right. This is an arrow pointing to the right. On the left-hand side, positives are moving away from you. On the right-hand side, positives are coming towards you. So if you can take a hitchhiker hand, make it so that your fingers are coming towards you when they're on the right, you're going to get that your thumb is pointing down. That means that this coil turns into an electromagnet with a north down here and a south up here. So the magnetic field lines would be going kind of like this way. Since this part of the coil, this coil creates a north down here and a south up here, this north would get attracted towards that south pole, and this south would get attracted towards that north pole. So if we put the coil in between a north and a south, the coil basically turns itself into an electro bar magnet, and the electro bar magnet means it's going to pivot. Whichever end ends up being south is going to get attracted to the permanent magnet's north pole. Whichever end ended up north gets attracted to the permanent magnet south pole. The way this particular one is drawn, the way it's going to spin is the coil is going to kind of go counterclockwise. It's really tricky for me to explain motors without an actual motor and things like that. So what I would like for you to do is check out this online explanation. There's some text there to read through and watch the animated video. It does a pretty good job of explaining motors. In a perfect world, you could look at one and maybe figure out which direction the motor spins. That's as far as we would ever get to in grade 11 physics in a normal year. For now, all I would like you to be able to do is look at this crazy thing and comprehend that that is what a motor looks like. And Yeah, that's good for motors. I know that motors are confusing and I didn't do a great job explaining them in this particular video. So check out these additional resources and see if motors can make a bit more sense. So you've got this one linked over here, and you've got this one linked down here. There is a fourth application. It's kind of the most important one. This one we'll spend a bit more time on. Uh, that last application is called transformers. So we'll pause this video, take a look and see if you can figure out electric motors, and then finish the note by learning about transformers.